In this video, we're going to go through another example of how to use trig substitution. And we're going to be looking at the example of the integral 1 over 1 plus x squared. Now, as you know, so far using trig sub, we've always kind of considered cases in which we're using trig sub to basically help us get rid of some square roots under the integral when we see x squared type quantities. Now, you'll notice this integral doesn't seem to have any square roots in it. However, we're going to see that because we still have this form of a Pythagorean identity, namely we have some constants plus some term squared in terms of our variable, we're able to use trig sub with that identity to help us out. And now, full disclosure, this example is basically going to tell us how to get the arctan or how to get the antiderivative to show that it's actually arctan in this case. Because you might remember from just Calc A that if we come across and take a derivative of arctangent, what we actually get is 1 over 1 plus x squared. So if you remember this derivative relationship, you should be able to see, oh, well, this integral should give us an arctan. But we're going to explicitly show how that's possible using trig sub in this example. So, name of the game here is using trig sub. The first thing, of course, we get to do is determine the correct substitution. And then on that note, make the substitution as well. So let's take a look at our possible substitution options. Now, what we see from this integral is we have this 1 plus x squared type term. So in this integral, the thing that jumps out to me is I have a plus sign there. And because of that plus sign, it's leading me to a particular identity, namely this middle one in terms of tangent. So it looks like I should be making a tangent substitution because we have that plus sign in that type of Pythagorean relationship. And in this case, the only constant we have there is a 1. So our constant a in this case would be a 1. And our substitution then is, well, x equals tangent theta. That 1 there is just to show that we could have had a constant, but in this case, it's just 1. So the next thing we could do when changing variables in an integral is start to go to that process of changing the dx from our original integral in terms of something in terms of our new variable, which is theta. And we do that by taking the derivative, dx d theta, in this case is, well, secant squared theta. And then when we just solve for dx, we can just cross multiply that d theta over, and we get dx is equal to secant squared d theta. So these two things now at our disposal, we have x is equal to tangent, and we have that dx is equal to secant squared d theta. We can go ahead and substitute those into our integral. So anywhere there's an x, we replace that with a tangent theta. And anywhere there's a, well, dx, we replace that with a secant squared d theta. So remember the secant squared d theta, that was our original dx. And that tangent is really what we're calling x from our substitution. So let's go ahead and just start doing a little bit of algebra to clean this thing up. So we have a 1 over 1 plus tangent squared theta in that denominator. And in the numerator, well, we could just put that secant squared theta. And of course, this integrals with respect to d theta. So at this junction, we can start employing some of our trig identities, namely the Pythagorean identity. And the useful one that we see is, well, whenever we have a 1 plus tangent squared, we could equally call that a secant squared. So if we make that substitution using our trig identity, 1 plus tangent squared theta is secant squared theta, we see a very nice thing actually happens in this case. The secant squared from the numerator and denominator cancel out, and the integral we get to do at the end of the day is just the integral of 1 d theta. And that is our trig integral we get to do. Now, it doesn't really look like a trig integral. Of course, it's still in terms of the theta variable. But we can, in a very nice way, compute this antiderivative of just 1 d theta. So the antiderivative of 1 d theta is, of course, just equal to theta plus c. Now we're almost done with this problem, except we still have one more act to go for trig sub. Our antiderivative that we just found is in terms of theta, but we need to go back in terms of our original integration variable x. So the third part for trig sub, convert back to the original variables. Which in this case means going back from theta to x. And now normally recall that we always start off here with our substitution. Our original substitution that we made was that we had x was equal to just tangent of theta. And I always like writing these substitutions in terms of the trig function. Namely, tangent theta is actually equal to, in this case, an x and well over 1. And the reason I like doing that again is if we're going after our right triangle, we know that, well, tangent is opposite over adjacent. So we know what two sides of that triangle immediately are. So in this case, if we're going to make a triangle, we would know that the opposite side is equal to x and the adjacent side is equal to 1. And then using Pythagorean theorem, we can know that this other side would be equal to 1 plus x squared. However, when we go back and look at what our antiderivative was, our antiderivative was just in terms of theta. We didn't have any tangents of theta, sines thetas, any trig functions of theta. So actually, in this example, we didn't really necessarily need to make this triangle at all, but I hope this was a little bit of extra practice for you. So since we have a single theta by itself, we get to use the inverse trig functions to help us tell us the identity of theta in terms of x. And the way we do this is we go back to our substitution, where we have tangent of theta is equal to x by itself. And remember, what we're after here is this theta value. And the way in which we can get theta by itself in terms of x is if we just come across here and use the inverse tangent of both sides. So taking the arctangent of both sides of this equation, we will be able to get just what theta is in terms of x by itself. So again, we just took the arctangent of both sides. Well, the arctangent of tangent just gives us back the argument inside of that tangent, which in this case just means that left-hand side reduces completely down to theta. And the right-hand side, well, the arctangent of x, that's just the arctangent of x. So what we found for this case, again, going back to our antiderivative up above, is what we saw was, well, to remind ourselves, we had the original integral of 1 over 1 plus x squared dx. We eventually saw through our trig sub that this was equal to theta plus c. I'll just say trig sub. And then lastly, when we went back to the original variables, we saw that this is actually equal to the arctangent of x plus c. And that is how sometimes we can use trig sub on integrals that don't involve square roots, but still have some number plus x squared stuff. in the form that we could eventually mathematically massage this into using our Pythagorean trig identities.